On the 9th of January, 1857, the San Andreas Fault tore open across roughly 220 miles of Southern California. In a matter of seconds, the two sides of the ground slid past each other by up to 30 feet. Rivers left their beds. Trees were snapped clean off at the trunk. It remains one of the largest earthquakes ever recorded in the United States, and for most of the 220 miles, nothing stood in its way. Then it stopped. Not because the fault ran out. There were hundreds more miles of loaded, ready San Andreas stretching south ahead of it, fault that had been storing strain for just as long as the section that had already broken. The rupture stopped at one specific place, a break in the mountains northeast of Los Angeles called Cajon Pass, and it did not cross. 45 years earlier, a different rupture reached that exact same junction. This was December of 1812, and it did not stop. It went straight through, and in going through it, pulled a second entirely separate fault system into the same event. Same location. Same faults sitting on either side of it. Two completely opposite outcomes. For a century and a half, nobody could explain the difference. That might sound like an academic curiosity, a footnote for seismologists, but it is not. It is arguably the single most consequential open question in American earthquake science, because whichever way it resolves next time decides whether the big one everyone talks about is a very large, very serious earthquake, or something in a category the region has not experienced since it held 20 million fewer people. In June of 2026, a research team published the first model that gives a physical answer to that question. And what the model finds, when you read past the headline, is that the gate looks open right now. Before any of that makes sense, you need the fault itself, because the San Andreas is not what most people picture when they hear the name. It is not a crack that is going to split open and swallow a city. It is a boundary between two enormous pieces of the planet. On one side sits the Pacific Plate, on the other, the North American Plate. They are not colliding head-on, and they are not pulling apart. They are grinding past each other sideways at a rate of roughly 2 inches a year, which is close to the speed your fingernails grow. That sounds almost gentle, and it is the entire problem. Two slabs of crust trying to slide past one another at fingernail speed, and mostly failing to do it smoothly, because friction locks the surface rock together even while the deeper rock underneath keeps moving regardless. The strain that should be released as smooth, continuous motion instead has nowhere to go. It accumulates, stored as elastic energy in solid rock, in exactly the way energy accumulates in a stick you're bending slowly with both hands. For a long time, there's no visible sign anything is happening. Then the stick simply cannot bend any further, and everything stored inside it releases at once. Los Angeles sits on one side of that boundary. San Francisco sits on the other. They are drifting toward each other at that same fingernail pace, and in about 20 million years, they will effectively be neighbors. Nobody needs to lose sleep over that part. What should keep people's attention is narrower and much closer in time. The southern section of this fault has not let go in a major way in more than 160 years, and the strain feeding into it has not paused for a single day of that entire century and a half. Start with the earthquake that is easiest to picture, because knowing how big it actually was makes the place it stopped far more interesting. The Fort Tejon earthquake struck on that January morning in 1857. The rupture front ran for roughly 220 miles down the southern San Andreas. In places, the ground on either side of the fault line displaced by close to 30 feet in a matter of seconds. The Kern River was knocked out of its channel. Shaking was reported across most of the state. California, in 1857, had a total population of around 400,000 people, and almost none of them lived in the region. The rupture tore through. The fault broke through country that was largely empty rangeland, which is the only reason this earthquake is remembered today as a geological event, rather than a mass casualty disaster. Had the same rupture happened in the same place today, the outcome would look nothing like 1857. Then the rupture reached Cajon Pass, and there, whatever it encountered, it could not get past. The San Andreas segments running south of that junction, the sections that continue on toward San Bernardino and down into the Coachella Valley, never moved. That single detail is the reason this story matters today, because those southern segments have been sitting there ever since, locked, still loading, never released. Every bit of strain the 1857 rupture failed to discharge on that stretch of fault is still sitting in the rock right now, more than a century and a half later. 45 years before that, in December of 1812, something different happened at the same intersection. A rupture arrived at the Cajon Pass junction, and it did not stop there. In the language the 2026 study uses, this is classified as a tripartite junction rupture, meaning all three fault sections that converge at that point move together in a single event. One earthquake, two separate fault systems at once. This comparison is the whole reason the question exists in the first place. The 1812 event was very likely smaller in raw magnitude than 1857. It did not release as much energy along as much fault length. And yet, it did the one thing the far larger 1857 rupture failed to do. It crossed the junction and kept going, which means the size of an earthquake, on its own, is not what determines whether that gate opens. Something else decides it. Work out what that something is, and you stop guessing about the largest plausible earthquake scenario for Southern California. You start calculating it. If you have ever driven Interstate 15 north out of San Bernardino toward Las Vegas, you have gone straight through Cajon Pass without necessarily registering what it is. It is a natural break in the mountain range, with a freeway running through it, a rail line, high-voltage transmission towers, fuel pipelines, and on any ordinary weekday, heavy traffic moving in both directions. Almost nobody crossing it has any idea what sits underneath. What sits underneath is the meeting point of two of the most active fault systems in North America. The San Andreas approaches from the northwest. The San Jacinto Fault, a separate system with its own rupture history and its own major earthquakes, comes up from the southeast. At Cajon Pass, the two intersect. Here is a detail that tends to surprise people the first time they hear it. There's no continuous crack running along the surface connecting the two faults. You cannot walk out into that landscape and physically trace a line from one fault onto the other. Whatever links them is buried well below the surface. And in the scientific literature, it is described as a mechanical interaction at depth, rather than as a single continuous structure you could point to on a map. That is precisely why it behaves less like a corridor and more like a gate. A rupture arriving at that junction cannot simply continue in a straight line. It has to jump from one structure to a mechanically distinct one. Sometimes that jump succeeds, sometimes it does not. Junctions of this kind have a specific name in earthquake science. They are called conditional barriers, not solid walls that always stop a rupture, not open doors that always let one through, barriers whose behavior depends entirely on the state of the surrounding system at the exact moment a rupture arrives. To answer the question of what state that system is in right now, you need to know how much stress is currently loaded onto each of the three fault sections that meet at Cajon Pass. That turns out to be a genuinely difficult problem, because stress accumulating deep in rock produces no visible signal. There's nothing to photograph. From the surface, the fault simply appears to be doing nothing at all. So the research team, led by Lilian Burkhardt, working across the University of Bern and the University of Hawaii at Manoa, along with colleagues from the United States Geological Survey and the Scripps Institution of Oceanography, approached the problem indirectly. They built a physics-based model of the full earthquake cycle in 3 spatial dimensions, then ran that model forward through time, which effectively makes it 4-dimensional. For a model like that to mean anything, it needs to know when each section of fault broke in the past, because every past rupture released the stress that had built up on that section and effectively reset the clock. So the team fed it a full 1,000-year history of ruptures across the region, reconstructed from multiple independent geological methods, radiocarbon dating of sediment layers disturbed by ancient ground movement, tree ring records from living trees that were damaged when the ground shifted beneath them, and written historical accounts covering roughly the last 2 centuries. They then let the model run forward from 1,000 years in the past up to the present day, adding stress at the rate the 2 tectonic plates are actually observed to move, and removing stress from a given segment every time the geological record indicated that segment had ruptured. What comes out at the far end of that process is a stress estimate in megapascals for each individual fault segment, current as of the year 2025. It is worth being precise about what that number actually is and what it is not. It is not a direct measurement taken in the field. It is the output of a model, and its accuracy depends heavily on the underlying 1,000-year earthquake catalog being approximately correct. But it is not a guess either. It relies on the same category of physics used in structural and seismic engineering, the same kind of modeling that informs how buildings and bridges near active faults are designed in the first place. The numbers that came out of that model are the reason this study made international headlines through the summer of 2026, and they deserve to be laid out precisely because the specifics matter more than the general impression. Stress is measured here in megapascals, a unit of pressure, and the raw number on its own tells you very little. What matters is comparison. For each of the 3 fault sections converging at Cajon Pass, the research team established a historical range of stress at which that particular segment has failed in the past, based on the reconstructed 1,000-year catalog. Then they compared that historical failure range against the modeled stress sitting on each segment today. On the Mojave South segment of the San Andreas, the stretch of fault immediately north of the junction, the historical failure range runs from roughly 1.2 to 2.7 megapascals. The modeled value for 2025 comes out at 2.8. That is not close to the top of the historical range. It is past it. On the North San Bernardino segment, also part of the San Andreas system, the historical failure range runs from around 0.4 up to 1.6 megapascals. The current modeled value is 1.8, again above the top of the historical range. And on the San Jacinto-Bernardino segment, the section belonging to the separate San Jacinto fault system, the historical failure range runs from roughly 1.2 up to 2.9 megapascals. The modeled stress for that segment today comes out at 3.6 megapascals. That is not merely above its historical range. According to the study, it is the highest stress value recorded anywhere across the entire 1,000-year reconstruction, on any of the three segments at any point in the modeled record. It exceeds even the reading from just before that same segment's previous major rupture, roughly 50 years earlier. The sentence from the paper that ended up traveling furthest through the press coverage was simple. Stress levels on multiple fault segments are now at, or above, the highest values recorded anywhere in the past 1,000 years. This is exactly the point where a piece like this usually stops being careful, so it is worth slowing down here rather than speeding up. Sitting above a historical failure range does not mean a fault is about to rupture. These thresholds are not precise trigger points. The very same segment has failed at meaningfully different stress levels at different times in the historical record, and there is no physical law stating that a fault must break the instant it crosses some fixed numerical line. What the finding actually establishes is narrower than an imminent warning, and it is still serious on its own terms. The system, right now, holds more stored energy than at any point the researchers can reconstruct. Which brings the story back to the original question: what actually decides whether a rupture crosses that junction? The intuitive guess is that a larger earthquake simply forces its way through, and a smaller one runs out of energy and stops. That guess is already contradicted by the historical record, because 1857 was an enormous rupture, and it stopped, while 1812 was almost certainly smaller, and it crossed straight through. The answer this model produces instead is stranger and considerably more specific. It is not primarily about how much total stress sits on either fault. It is about how similar the stress levels on the two sides of the junction are to each other. When one fault system is heavily loaded, and its neighbor across the junction is not, a rupture arriving at that boundary runs into a section of fault that is nowhere close to its own failure point, and the rupture simply loses momentum and stops there. When both sides are loaded to roughly the same degree, relative to their own individual thresholds, the rupture instead arrives at a neighboring section that is already close to failing on its own terms, and it pulls that section into the same event. Put simply, the gate does not open because of raw force. It opens because of agreement between the two sides. This is precisely why the 2026 findings are unsettling to people who study the system closely. It is not only that stress is high. High stress on its own has happened before without producing a joint rupture. What is different this time is that stress is high on all three sections converging at that one junction simultaneously, and the gap between them is small. According to the researchers' own past reconstruction, historical through-going ruptures at Cajon Pass have occurred when the stress difference between the San Jacinto-Bernardino segment and the Mojave South segment narrowed to somewhere around 0.3 megapascals. As of the current model run, that gap stands at roughly 0.8 megapascals, not identical to the historical crossing condition, but measurably closer to it than the system has been recorded to be at any other point in the reconstructed 1,000-year history. In the author's own words, this convergence of high, closely matched stress across the junction makes it more likely that Cajon Pass could transmit a rupture from one fault system directly into the other. As far as the model can determine, the gate right now looks open. It helps to walk through what that would actually look like, and this part is a scenario built from how ruptures are known to behave physically, not a forecast of a specific future event. It begins as a small patch of fault losing its grip, an area only a few miles across. Earthquakes do not start everywhere along a fault at once. They start at a single point and then spread outward from it. The rupture front then travels outward along the fault at somewhere around 1.5 miles per second. That is faster than the shaking it produces travels, and that single detail is what separates a large, long earthquake from a small, short one. In a small earthquake, the ground shakes for a few seconds, and then it is over. In a rupture that runs for 100 miles or more, the shaking is still arriving in one location, while the tear in the crust is continuing to spread somewhere else entirely. And it keeps arriving for as long as that tear keeps extending. That is why survivors of large ruptures consistently describe duration rather than intensity as the defining feature of the experience. Not how violent any single moment felt, but how long the ground simply refused to stop moving. For a rupture of this scale, the shaking in the hardest hit areas is expected to last somewhere between 1 and 2 minutes. Stand still and count out 90 seconds, and picture the floor beneath you not settling for the entire span. Within roughly the first minute, the rupture front reaches Cajon Pass. If it stops there, the result is still an extremely large Southern California earthquake, broadly comparable in scale to 1857, and the fault segments south of the junction remain locked, still holding everything currently stored inside them. That alone would be a historic disaster. If it crosses instead, the event stops being a San Andreas earthquake and becomes a combined San Andreas and San Jacinto earthquake. And that is the point where geography stops being an abstract detail and becomes the entire story. The San Jacinto Fault does not run through empty land. It passes directly beneath San Bernardino and Riverside, through some of the fastest growing urbanized areas in the entire country, continuing on in the direction of the Coachella Valley. The 1857 rupture tore through country that, at the time, was almost entirely unpopulated. A rupture following that same San Andreas path today would already be moving beneath a metropolitan region of well over 20 million people. And if the gate opens this time, the rupture does not even follow that same single path. It takes a longer one, crossing beneath considerably more of them. There is a second reason this specific junction matters so much, and it has nothing directly to do with buildings collapsing. Southern California's water, power, and fuel are not routed around the San Andreas Fault. They are routed directly across it. The aqueducts carrying water from the Colorado River and from Northern California cross the fault line. So do the region's major electricity transmission corridors, its fuel pipelines, its natural gas lines, the interstate highway itself, and the primary rail freight route serving the entire basin. All of that infrastructure was built through Cajon Pass for the same simple reason. The terrain allows a route through the mountains there, and the terrain allows it because two faults spent millions of years grinding and opening through solid rock. That opening is now filled with nearly every critical supply line, keeping a region of millions running day to day. A rupture through that junction does not simply shake Los Angeles and San Bernardino. It severs several of the lifelines that those cities depend on, all at once, within the same few miles of ground. The collapsed buildings are the part that ends up on television. The severed lifelines are the part that actually determines how long the aftermath drags on. And Southern California's infrastructure planners have been quietly aware of this vulnerability for decades. Reinforcing pipelines, transmission towers, and aqueduct crossings against a scenario like this is expensive and slow, and it competes for limited funding against emergencies that are already happening today, rather than a disaster with no fixed date attached to it. To put a number on the stakes, it helps to look at the existing planning scenarios that emergency agencies already work from. The United States Geological Survey's shakeout scenario, built around a magnitude 7.8 rupture on the southern San Andreas alone, without any involvement from the San Jacinto Fault, estimates roughly 1,800 deaths, 50,000 injuries, and something in the neighborhood of $200 billion in direct damage. That is the baseline scenario planners already treat as a realistic worst case for a single fault event. What this new study raises is a scenario sitting above that baseline. A joint rupture in which the San Andreas and San Jacinto systems fail together through the same junction in the same event. The 2286 study does not attempt to model a specific death toll or dollar figure for that combined scenario. What it does establish is the physical configuration under which such a combined rupture becomes plausible, and it argues that Southern California's fault system is currently sitting closer to that configuration than at any other point in the reconstructed 1,000-year record. Which brings the story to the part that most coverage of this study left out, and it comes directly from the lead author. Asked plainly what the findings actually mean, Liliana Burkhardt was clear that this is not a prediction of when an earthquake will occur. What can honestly be said, in her words, is that the system is critically stressed, and that models of this kind give researchers a clearer picture of the range of scenarios that need to be prepared for. That distinction is the entire difference between a piece of science and a piece of clickbait, and it is worth stating plainly rather than skating past it. The model cannot tell you when. It was never built to tell you when. What it can tell you is how much stored energy currently sits in the system, and which configurations of that stored energy have historically produced through-going ruptures rather than contained ones. Whether the next major event happens in 11 months or in 80 years sits entirely outside what this method is capable of saying, and the researchers themselves make no claim otherwise. There is also a genuine limitation built into the method itself, and the authors are upfront about it. The entire model rests on a 1,000-year earthquake catalog reconstructed from sediment layers and tree rings, and that catalog inevitably contains gaps and dating uncertainties. Feed the model a slightly different version of that history, and the present-day stress numbers shift. This is a range of plausible scenarios grounded in the best available reconstruction, not a countdown clock. And there is a version of this story that tends to get told badly, and it is worth naming directly, because it shows up almost every time research like this reaches a wider audience. Periodically, a study like this one gets reframed as an imminent specific warning. When the following year passes without a matching disaster, the public reasonably concludes that scientists were exaggerating the danger. That reaction is not harmless. It quietly erodes the case for funding preparation work aimed at an event that, sooner or later, has essentially a certainty of eventually happening, just without a fixed date attached. So what would actually move this question forward? Not prediction. Serious researchers in this field largely abandoned the goal of predicting exact earthquake timing decades ago for well-established reasons, rooted in how chaotic the underlying rupture process is. What is genuinely being worked on is narrower and considerably more useful in practice. Better paleoseismic records, meaning more trenches dug directly across these fault lines to locate and precisely date additional past ruptures, which sharpens the historical catalog the entire model depends on. Denser satellite and ground-based measurement of how the surface is actually deforming right now, which lets researchers test whether the modeled strain matches what is physically observed. And better physics, describing exactly how fault junctions like this one behave, which is the specific contribution this 2026 paper makes to the field. None of that will ever tell anyone a date. All of it tells engineers, planners, and emergency managers what to build for. And there is a version of this future in which the gate eventually does open, and the outcome is measured primarily in disruption rather than in loss of life, because the infrastructure crossing that fault line was reinforced well in advance. That outcome is not decided by geology at all. It is decided by budget decisions made years or decades ahead of time for an event that carries no date on it. Go back to that January morning in 1857 one more time. A rupture 220 miles long tore down the fault, reached that break in the mountains, and simply stopped. Nobody today knows how close it actually came to jumping that junction. That is not a rhetorical flourish. There is no way, from outside the event itself, to measure how near a rupture came to crossing a gate it ultimately failed to cross. What is known is that everything that rupture failed to release on the far side of that junction is still stored there. The sections on both sides of Cajon Pass have been loading continuously for more than a century and a half since. And the disparity between them, the specific quantity the model identifies as the thing that ultimately decides whether the gate opens, is currently smaller than it has been at almost any other point across 1,000 years of reconstructed history. The fault itself is not waiting for anything. It has no schedule, and it holds no intention. It is two enormous pieces of the planet sliding past each other at roughly the speed your fingernails grow, and with every day that passes, the stick bends a fraction further. The only real question left is which side of that gate the next rupture ends on.